Now that we've had our introduction to specific heat, we've learned our vocab, we've gone through a couple of concepts, we're going to go through several practice problems. So for this first one, we want to know how much energy is required to heat 50 grams of water from 20 degrees Celsius to 80 degrees Celsius. And it even tells us the specific heat capacity of water is 4.184 joules per grams degrees Celsius. So remember, specific heat, we're talking about how much energy does it take to heat 1 gram by 1 degree Celsius. So it depends on grams, it depends on how much you're trying to raise it, and you will need that specific heat to relate those concepts. So we have our formula right here, that Q is equal to MC delta T. I'm going to go ahead and pull out what we already know, and I've already done that. First, our mass, which is that M, is 50 grams. C, which they gave us, that was the specific heat capacity, is 4.184. And then our delta T, that is our change in temperature, and it's measured in Celsius. So the first thing you need to know is that's T final minus T initial. So because our temperature is increasing from 20 to 80, 80 will be our final temperature, 20 is our initial, so 80 minus 20 is 60 degrees for that delta T. At this point, we can just plug everything in, and you'll notice that all of our units will cancel out except for that joules. So our answer will be given in joules. When we plug that all into our calculator, we get 12,552 joules. Or if your answer choices are given in kilojoules, or if it asks you to give it in kilojoules, you could just move that decimal place 3 spots to the left to get 12.552 kilojoules. Or if it helps you to set up your little conversion right here, you can do that as well, whatever is easiest for you. So take a second, make sure you know how to apply this, and we're going to do some more examples. For our next example, it tells us 4,000 joules of heat energy is applied to a 70-gram sample of water, which is initially at 35 degrees Celsius. So we want to know that final temperature of the sample. And then once again, it gives us what our specific heat is for this, and it's the same as it was in the previous problem. So now we're going to go ahead and set that up. Q is equal to this MC delta T. That hasn't changed. I went ahead and pulled out what we know. So this time we have our Q value, that's how many joules of energy is required. We have our mass, which was 70 grams. We still have our specific heat for water, that hasn't changed. But now that delta T is a little bit different. So delta T, which is T final minus T initial, we only have the initial. So we're solving for that T final. So what I did was I went ahead and put this delta T on the left-hand side by itself, and I did that by dividing Q by M times C, and then I kind of broke apart delta T. I know it's T final minus T initial, so I just added that T initial to the right side to get this equation. I find it easier personally to rearrange my different variables to get what I need by itself on the left-hand side first before I actually plug in the numbers. If it's easier for you to just go ahead and start working with the numbers, then that's totally fine. This is just what works well for me, so I wanted to show you what it looks like. So now that I have my T final on the left-hand side, I just go ahead and plug in all of my numbers. It's Q over MC plus T initial. And what we get at the end is 49 degrees Celsius. And this makes sense. Basically what you're doing is you have an initial temperature, you're adding some amount of thermal energy to a certain sample with a certain specific heat, and you should get what the final temperature is. So 49 degrees Celsius was our final answer. Take a second, if you need to pause the video, copy down any notes, you may do so, and then we'll continue on. Okay. Our next problem, I just wanted to introduce another concept that might help you as well. So we still have our formula at the top. The Q is equal to MC delta T. And remember, our delta T is T final minus T initial. So let's think about this for a second. If our T final, if that final temperature is lower than the initial temperature, you'll notice that our delta T, that change in temperature, will be a negative number. If that delta T is a negative number, then our Q will also be a negative number. And same goes for the opposite. If our final temperature is higher than the initial temperature, then our delta T, that change in temperature, will be positive, and our Q will be positive. So tying that back to something we already know, if our Q is greater than 0, meaning if it's positive, we consider that to be an endothermic reaction because we are adding heat. That T final is greater than T initial. If that Q is less than 0 or negative, we consider that to be exothermic. We're removing heat. That T final is going to be lower than the T initial. So endothermic and exothermic will still apply when we do our lessons today. For this next practice problem, we have a 100-gram sample of an unknown metal, which is 150 degrees Celsius. And it's dropped in a bucket containing 50 grams of water, initially at 21 degrees Celsius. The final temperature of the mixture was 32 degrees Celsius. So we want to know the specific capacity of the unknown metal. This seems a little overwhelming at first. We're going to break it down and explain each step. So first, I wanted to show you, I did a little diagram right here on the left of maybe a beaker or a cup. And we have this unknown sample, this metal, which is at 150 degrees Celsius. And it's dropped into the water, which was initially at 21 degrees Celsius. Now we know that our heat always moves from higher temperature to lower temperature. So the heat will be going out of that 150 degrees and into that 21 degree water until it equals out and they're both at 32 degrees Celsius for the mixture. So what does that tell us? The water, the temperature is going to increase. It's gaining heat energy, so it is considered endothermic. That Q is going to be positive. The metal, on the other hand, it's losing heat. It's giving away that heat to the water and it's releasing it. So our Q will be negative. Now I'm going to show you a new formula that's going to help us solve this one. It's very similar to what you already know, but in this case we say QA is equal to negative QB. So they're going to balance out because they're joining into one system. How do I know which one is which? Notice QA is positive, so that is the endothermic portion. In this case, that's the water because the water is gaining that heat. The negative side is going to be our exothermic portion of the reaction. So our exothermic portion was that metal because it's losing that heat. So QA is equal to negative QB. And we already know that Q is equal to MC delta T. So we can just plug that in. MC delta T is equal to the negative of MC delta T for the metal. Don't forget that negative sign. It will be important later on. So at this point, I went ahead and started plugging in values. We have the mass of the water, 50 grams. We have the specific heat of water that we've used in the last two problems. And then we have that change in temperature. We know the final temperature will be 32 degrees Celsius, but the water was initially at 21 degrees Celsius. And then on the right-hand side, I have a negative sign. I didn't lose that. My 100-gram sample of the metal, the specific heat of the metal, which we don't know yet. We're trying to solve for that. And then the temperature change, that delta T. Our final temperature was 32, and our initial temperature was 150 degrees Celsius. So notice that 32 minus 150, it's going to give us a negative number. And because of that, when you have this negative number times this negative number, because it's negative 100 right here, you will get a positive. Just like you've learned in algebra, that's still the same thing. So when I multiply the left-hand side out, I get this 2301.2 joules. And then when I multiply the right-hand side out, I get 11,800 grams degrees Celsius. So how did I get my units? Just like we've done before, MC delta T, if you have all of those values, everything is going to cancel out except for that joules. On the right-hand side, all I have is grams and degrees Celsius. That's totally fine because we are not solving for it just yet. But notice, when I divide my left-hand side by that right-hand side to get the specific heat of metal by itself, that C of the metal, I will get something that is in joules per grams degrees Celsius, which is just what a specific heat is. So that's how this works out. You divide the left-hand side by that right-hand side, and your C of the metal, or your specific heat of the metal, is 0.195 joules per grams degrees Celsius. So I'm going to zoom out so you can see that. Take a second. I know this is a little bit more challenging than the first portion was. Take whatever notes you need to, and make sure that you understand it before we move on. Okay, now our last problem. I know it's been a longer section, but I want to make sure you understand this concept. For this one, we have 18 grams of calcium chloride, and it's dissolved in 150 grams of water at 20 degrees Celsius as shown in the reaction. The specific heat capacity of the solution is 4.18 joules per grams degrees Celsius. We want to know what the final temperature of that mixture was when we combined them. So the first thing I need to do, we are given this reaction right here. This should look very familiar from when you were working with enthalpy. So we have calcium chloride breaking apart into those ions in water, and that delta H, or that change in enthalpy, is negative 81.5 kilojoules. So remember, if it's a negative number, that tells us that it is exothermic. It's giving off that heat. So that reaction is losing heat energy. I went ahead and found my molar mass for calcium chloride because I know we're given an 18-gram sample, but you can only use moles when working with this reaction. So I need to convert those grams to moles. So that's what I went ahead and started to do. I took my 18-gram sample of calcium chloride. I multiplied by 1 mole of calcium chloride is 110.984 grams. Notice my grams will cancel out there. And then I knew a few more things. I know that for every 1 mole of this reaction, we get negative 81.5 kilojoules of energy released. So my moles will cancel out now. And then because we're working with joules as our unit, when we're working with Q, I went ahead and simplified my kilojoules to joules. I just multiplied 1,000 joules over 1 kilojoule to cancel out my kilojoules, and I'm left with joules. So the Q of this reaction is negative 13,218 joules. So just like that delta H, that enthalpy was negative, telling us it's exothermic, that Q is also negative, so we know it is exothermic. It's giving off that thermal energy, which is absorbed by the solution. So because that energy can only go one place, it can only go into the solution it's creating, our Q of the solution is exactly the opposite. It absorbs every bit of that energy that reaction releases. So Q of the reaction, negative 13,218 joules. Q of the solution is positive 13,218 joules. So now I know my Q for the reaction. I know my mass of the reaction. The mass is just the mass of the water plus the mass of the sample. My C, which it gave me, that's my specific heat. I don't know the final temperature, but I do know that the initial temperature was 20 degrees Celsius. So we're going to solve for that final temperature. So once again, I have Q is equal to MC delta T. I went ahead and simplified it like I did before to get T final by itself on the left, and then I have the rest of the variables on the right-hand side. At that point, I just plug everything in like I've done before. My final temperature is about 38.82 degrees Celsius. I went ahead and simplified it to 2 significant figures. So our final temperature is about 39 degrees Celsius. Notice this is what we expect. We know that this reaction is exothermic and gives off heat. We know that it was initially 20 degrees Celsius, so we would expect it to increase in temperature since it's absorbing that heat. Take a second, make sure you understand this, and then you'll answer some questions on your own.